Hello, I'm Seth Daly, and this is a Calculation Success Module Skills video. Today we'll be talking about active drug moiety calculations. If you want to follow along in the textbook we use, it's Chapter 20 of Stocklessa and Ansell's Pharmaceutical Calculations. Let's get started. So, active moiety. So drugs are usually formulated, and they can be formulated as esters, or salts, or hydrated. And the reason is it's to help the pK or the PD of the drug, okay? And that's why they're formulated. Now, the formulated API always has a higher molecular weight, or grams per mole, than the API base, always. And this will really, really help us out when we're doing our math if we can keep that in mind. So here's an example. This is tetracycline, okay? So this is tetracycline base. And it has a molecular weight of 444.44 grams per mole. On the right is tetracycline acetate, okay? So it's formulated with a HCl, an acetate, and a water. And when it's formulated, there's actually 2 molecules of tetracycline for every mole, okay? And that's why the molecular weight for tetracycline formulated is so much bigger because it has all these extra molecules, and the crystal structure of that powder actually has 2 tetracyclines for every molecule, okay? So the formulated is always greater than the base. So we have a question. If we have a 250 milligram capsule of tetracycline hyclate, how many grams of tetracycline base are contained in the dose? Okay. Now I see a lot of students struggle with these kinds of questions, and one of the things that I think can fix a lot of these things is labeling. Okay. So we have 250 milligrams of tet hyclate, okay? So I'm just making a quick shorthand. And I want to match the molecular weight of the tetracycline hyclate. So 102.5.89 molecular weight, tet hyclate, equals X milligrams of tet base, and we want to match the molecular weight of the tetracycline base. Okay, so when actually labeling these things, it doesn't take that much more time, but it assures that I make sure the milligrams of tet base go with the molecular weight of tet base, and the milligrams of tetracycline hyclate go with the molecular weight of tetracycline hyclate. I have milligrams on tops and molecular weights on bottom, so I'm ready to solve. So X equals 250 times 444.44 divided by 1025.89. So X equals 108.3 milligrams of tet base. But the question says grams, so we need to convert. We want to get rid of milligrams. We want to go to grams. Grams is bigger, so we divide by 1,000. And we get 0.1083 grams, okay? Now, how can we check if we're right? We always said that the formulated is bigger, okay? The formulated was 250 milligrams, and our base was less. So that's a really good self-check to make sure we're doing this right, okay? So, again, label your numbers, tag, and label. That will really help you solve these questions. All right, we can also use equivalent weights for active moieties. So here we're dividing by the valence of the active component. So the valence is the number of ions per molecule. So the valence for the tetracycline hydrochloride is 1, and the valence for the hyclate is 2. So Our molecular weight is 444 divided by the valence gives us the equivalent weight, and our equivalent weight is 444.44 grams per mole. Okay? Here, our molecular weight is 102.89, but it's per 2 molecules to give us the equivalent weight. And so here our equivalent weight is 1025.89 divided by 2 equals 512. Oops. This is why we have an eraser. Maybe. 0.9 grams per mole. Okay? And what the equivalent weights allow us to do is now, if I weigh out 444.44 grams of hydrochloride, I get 1 mole of tetracycline. And now, if I weigh out 512.9 grams of the hyclate, I also get 1 mole of tetracycline. So it's making our molecular weights equal. Okay? So we can also use it for ions in a solution. So the formula for 1,000 grams of a cream calls for 14.7 grams of potassium carbonate. So how many grams of potassium hydroxide could be used to replace the potassium in the formulating the cream? So if we look at potassium hydroxide, we assume a 1, and so our equivalent weight is 56 divided by 1, which is just 56. If we look at the carbonate, our valence is 2, so our equivalent weight is 165 divided by 2, which equals 82.5. Okay? And now we set this up just like an active moiety equation. If we want 14.7 grams of KCO3, and we know the equivalent weight is 82.5, and it's a molecular weight still, oops, of KCO3 equals X grams of KOH if the molecular weight equivalent is 56 KOH. So we would need 14.7 times 56 divided by 82.5. We would need 9.98 grams of KOH if we wanted to use KOH instead of K2CO3 for this. Okay? So same thing. This one just uses an equivalent weight to do the same math. If you have any questions on this, you can email me at sdaly@salud.unm.edu. Happy calculations.